Okay, thank you very much. Thanks for the introductions. Can you hear me? Well, yeah.
Yeah, perfect.
Okay, perfect. I want to start with the acknowledgements to the organizers to allow me participate in this online meeting. Today I'm going to talk about two recent findings that we have found in the heavy fermion system uranium-ruthenium-2 silicon-2. I'm going to start with the results of one-dimensional moiré pattern that we observed. A recent version of the analysis of these results have been recently uploaded to the archive. The history of the uranium-ruthenium-2 silicon-2 begins in 1985 with the reports of two transitions by resistivity and specific heat measurements. One transition at 1.2 Kelvin is identified and was confirmed as a superconducting phase, and the other below to 17.5 Kelvin, in which there is a large entropy change, was reported also. This phase is known as a hidden order phase because it is not clear the microscopic origin. And a lot of work on experimental and theoretical work has been focused to try to understand this phase, but after 35 years, we don't have a clear answer about the elementary excitations in this specific phase. And respect to the superconducting phase superconducting phase, there are references that point out of uranium-ruthenium-2 silicon-2 as a strong candidate for chiral superconductivity. So the uranium-ruthenium-2 silicon-2 is part of the heavy fermion family compounds. In these compounds, the electrons of the localized states hybridize with the conduction electrons, and this hybridization process generates the heavy bands. And the strong interactions between the localized and the localized electrons generated by this hybridization process can be measured using a scanning tool microscopy. And for the uranium-ruthenium-2 silicon-2, temperatures above of the hidden order phase, the density of the states can be fitted using the well-known Fana function. But decreasing in temperature and in energy inside of this Fano structure, we can see evidence of the hybridization process inside of this. In the case of the uranium-ruthenium-2 silicon-2, these features that we can see here and in these peaks are related or have been linked to the hidden order phase. And also, if we decrease in temperature below to the critical temperature and also in energy, we can see that we have evidence of the superconducting gap at very low energies. Now, the phase diagram of this system is very complex, and here I just want to put one of them as a function of the pressure and the temperature. But in the hidden order phase, neutron scattering experiments have shown that there are two dynamical spin excitations which are identified with these two vectors, Q0 and Q1. Okay, these vectors also identify another regions of the phase diagram. For example, here, the antiferromagnetic region also is identified with the same vector Q0. And here, a high magnetic fields, another magnetic phase, is identified with this Q1 vector. This is above 30 Tesla. So, but what about the hidden order phase and the Fermi surface? In this compound, the Fermi surface is reconstructed due to a nesting between the different parts of the Fermi surface. This nesting occurs precisely in this Q0 directions, and the overlapping of the two parts generates hotspot regions that we represent here with the yellow color on the KX-KY plane, and they are also connected with this Q1 vector that we have represented here with this. So this Fermi surface reconstructor, and then this allows the opening of gaps in different directions. Okay. So with all this small introduction of this system, we can say that the uranium-ruthenium-2 silicon-2 is a system with a high electronic and magnetic susceptibility, in particular in this both directions. Okay, this is the first part of the motivation. The second part is this one, as maybe all we know by own experience, is that in solids, a fracture produces permanent modifications on the crystal, okay? And some of them can be more evident on the crystal surface. These modifications can be due to the acoustic waves that are emitted when the crack front crosses defects during the cleaning process, or due to another local interactions of the crack front and the crystalline lattice, even when the crack front change directions between consecutive layers of the solids. These effects or modifications has been studied in materials such as silicon or tungsten, and with this known that the fracture produce permanent modifications on the crystals, and having this kind of exotic system, the question that we can try to ask is, can we create new ground states through a fracture process? And the answer is yes, and I'm going to try to show you how we create a new ground state using this cleaning the samples. So, but to do that, we need to first we need to have control of the cleaving process of the samples. And here I would like to introduce the experimental setup to cleave samples, to cleave hard samples at low temperature. These are pictures of the samples provided by Dayaoki, and here this is a picture of the sample mounted on the STM at room temperature. Here we have a picture from the top view of the sample, and here we have a schematic representation. The sample that we want to cleave is represented here by the red color. So we use a wire to pull the sample holder and hit the sample against the blade that is represented here with the blue color. And at the end, we got a clean surface, okay? And let me highlight here that all this procedure always was done at liquid helium temperature, okay, at 4.2 Kelvin. And after cleaving the samples at these temperatures, we got this kind of beautiful images that as you can see here in this profile, we have a square terraces, and the distance between consecutive terraces is exactly always proportional to a half of the unit cell in the z-axis directions. In these terraces, we have atomic resolution, and the interatomic distance of the square lattice that you observe here in this image corresponds to the distance that we have between uranium atoms. In fields of view, more bigger, larger, and fewer steps and defects, we observe that we have certain pattern which repeats on the image here, and you follow here the pointer, and it's one-dimensional. Okay, here in the Fourier transform, we can observe the usual bragg peaks for the square atomic lattice, but here at the center, we observe multiple peaks, which are with a distance that we call Q sub m, which is the evidence of this 1D modulation. The period of the modulation in the real space is 6 nanometers, and it corresponds to this value in the reciprocal space. So we observe the same one-dimensional pattern on 5 different samples after cleaving at low temperature. Here we have same images of all the samples that we have measured, and here we have topography images on each one of them. So as you can see here, we also have the same one-dimensional pattern, and even under different temperatures and different magnetic fields. So in all the samples, we observe the same 1D modulations with the same periodicity, 6 nanometers. We know that in a STM, when we observe this kind of phenomena, which is superimposed to the atomic lattice, it is caused by a charge order. So the next question is if we can establish a relation between this wave vector and the Q1 vector that we identify at the beginning that is on the plane. And how we can mix these two vectors? So the answer is using the moiré patterns. So as maybe all you know, the periodicity of a moiré pattern depends on the periodicity of the initial patterns. For example, here, the final pattern of overlapping these two patterns originates this pattern, but with a periodicity which is given by this expression. But a special thing happens here between the moiré patterns if the initial pattern has or have similar periodicities, as I show you here. And if the initial pattern satisfies these conditions, the resulting pattern is known as a fractional moiré pattern. And the periodicity will be given by this expression that I put here. So we use this to analyze our data. So let me show you here the model that we propose to create our model. Here we have a one-dimensional modulation, which is with this periodicity related with the vector Q1. And here we represent the atomic lattice with these dots, green dots. So this is the top of view, and this is a lateral view of the model. So here we model the atomic orbitals on each atom with these lobes, and the lobes represent the charge distribution on each atom. So the overlapping of these two of the modulation and the atomic lattice results in this pattern. Here we represent how the modulation changed the size of the lobes, as you can see here. And the size of the lobes leads to a pattern that can be fitted using two cosines, as you can see here with the red line and the blue line. And the cosines has the same periodicity, but they are shifted by pi. And this particular situation is a characteristic feature of the fractional moiré pattern. So with this, we can say that our images are shown a one-dimensional charge density wave with a periodicity Qn as a consequence of the combination between the Q1 vector and the atomic lattice in a fractional moiré pattern. So we observe this pattern because the STM tip is sampling this charge density wave effect on each atom. Now that we have the mathematics behind, so the next step is try to identify the physics, the origin of the modulation of this with this specific vector. And just let me start saying here that in previous STM reports by the group of Seamus Davis and Elijas Dani, they do not present the modulation, although the resolution is the same resolution that we have here as we represent with this bar here. But the main difference and the main point here is that in those experiments, the samples were cleaved at low temperatures outside of the hidden order phase, okay? Whereas in our case, we cleave the sample at liquid helium temperature, which is inside of the hidden order phase. So this led up to think about the cleaving process at low temperature. So to analyze this, the main difference, we know that we simulate here what happened when we cleave a sample. So cleaving a hard single crystal is a fast procedure by which the bonds are broken first in one side of the sample, and then the crack front travels through the sample in very short amount of time. For example, in our case, we calculate that the time is around some femtoseconds. And here we have the simulation of the cleaving process showing how the pressure distribution change on the crystal and also on the XY plane, as you can see here. So as I said in previous slides, the propagation of the crack front during the cleaving leaves permanent modifications on the surface. Okay, so let's check this and see what happened if we compare a sample that were cleaving at room temperature and another samples that were cleaving at lower temperature. Here we have the two examples. This sample here was cleaving at room temperature, and this sample was cleaving at lower temperature. I'm not going to enter in details here because the thing that I want to remark here is that when we measure, these are some images, when we measure around and in regions around some microns, as you can see here, the main difference is that on the sample that we cleave at low temperature, here, we have a set of linear features that were created during the fracture, and they are oriented closely to a crystalline axis, and as I put here to represent that they are nearly parallel to the atomic lattice with these purple lines. So, and let me remember that from our experimental results, the modulation that we observe is also nearly parallel to the crystalline axis or to the in-plane crystalline axis. So how we can explain this? What about the physics behind? Here it's important to notice that the lattice the studies of the lattice dynamics in uranium returning to silicon-2 shows that the energy scales, okay, the energy scales of the phonon modes, optical, longitudinal, acoustic modes, all of them has this kind of order of magnitude of energies. And also, the magnetic excitations, the electronic excitations represented here by Q0 and Q1 also are of the same order of magnitude that the other ones, which means that creates interactions between them. If we are in this range of energies, will be very, very easy. So we calculate that the dispersion relation for the Q1 mode is the order of kilometers per second. And the same order that we have for the crack front and also for the phonous modes. So therefore, this means that we can link together this the external action of the crack front, the atomic displacement, the phonons, and the electronic fluctuations at Q1. So from the Fermi surface point of view, we can see this interaction as a combination between the hot spots in the hidden order state close to Q1 vector and the atomic lattice. And this combination is due or is a consequence of the cleaving process that is represented here by the pink arrows. So we increase, when we cleave the crystal, we increase the interaction between these hot spots and the atomic lattice. And the result is that we get a new modulation. So the crack front is providing a one-dimensional breaking field, increasing the interaction between the lattice and the Q1. So therefore, we can conclude that the 1D modulation was originated during the cleaving process at low temperature, and that we have a QM vector is a moiré combination of the reciprocal lattice and the constant and the Q1 vector. So I invite you, if you want more details, to check our paper in arXiv. Okay, so let's move to the second part of the talk here, about which is related about to the direct observation or heavy Fermi quantization. I want to start here, just put this image where you can see here also the terraces, and here we have I show a video in which how change the density of states as a function of the energy. And as you can see, the pattern, how change the pattern, and we have here a standing wave pattern on the surface as a function of the energy. Let me put this in this form here. We plot just some of the energies as a function of the bias voltage, And you can see here just the kind of ripples of the waves on the different terraces that we get here. And to explain this, let me remind that the pattern that we observe here is so similar to patterns that has been observed in noble metals like copper and silver. And maybe the most popular standing wave pattern observed using a STM is this one, the quantum coral that was made by iron atoms on a copper surface. We have the same, but we don't have circular quantum corals, we have square quantum corals. So these patterns in the density of the states are produced by the scattering of surface electrons with barriers like steps in our caves or defects like this one. So let me explain a little bit with more detail what happened here in the previous reports. So the standing wave patterns is evidence of a two-dimensional electron gas. Okay, the two-dimensional electron gas occurs on surface of metals perpendicular to the directions where the Fermi surface has gaps. Okay, in the case of copper and silver, here we have the Fermi surface, and you can see here that we have a special gap in this direction, parallel in the direction that we are measuring with the STM. So from the analysis of the density of the states at each energy, we can see that this behavior corresponds closely to the physics that we have of an electron confined in a box of length L. Okay, here for the silver, there is another type of representation of the density of the states as a function of the energy and the distance. And here, and it's more evident the quantization in this case, where they represent the levels here with the quantum levels with the red lines. And let me put this here, okay? And let's back again to the experiment. So we focus our attention in this terrace, okay? Well, here we average the density of the states in this direction, parallel to the atomic lattice, okay? This is the result that we get, okay? And the first thing that we observe here is that we can identify a special background that we have in our experimental results. And here we have some levels of the quantizations, which we mark with the white dots, and we compare this with the calculations for electron in a box. And you can see here a good correspondence between the lowest quantized levels and the background that we have in our experimental result. So from here, the band structure is shown here with the red line, and we assume this classical free electron dispersion, and by using an effective mass of 17 times the electron mass, which is of the same order of magnitude of the previous report. So why we are observing this on this compound, and in particular in this type of surface? And as I described at the beginning of the talk, the Fermi surface is nesting in the 011 direction. And here, this nesting produces a gapping, which is also parallel to this direction. So it originates the two-dimensional electron gas, and also we are measuring in this direction. And the two-dimensional electron gas is confined due to the presence of these steps, okay? Here, we can also see that on top of the background, you observe these two features that enhance or increase the value of the density of the states at energies that are close to 0.4 millieVs and minus 1.4 millieVs. So these two features, in particular in these positions, are related to the low energy excitations that we have in the uranium-2 silicon-2. And also we have measured that excitation by using STM. And they are here, and they are known as Van Hoff singularities. And they connect the realization gap. but I'm not going to talk in detail about this. Just I want to say that we assume that the behavior of the Van Hoff singularities is constant with the distance, and here we simulate them as a two Lorentzian functions. And also, if we check a little bit with more detail the experimental result, we observe here also that we have increasing of the conductance just at the borders of the steps. And these two structures of the border are H states, okay? And they appears here because we have a redistribution of the electronic charge just at the edge of the step. And I'm going to talk to enter here also in detail. So we simulate the H states as a two-dimensional Gaussian functions, okay? And now we have all the three ingredients, and if we put all these ingredients together, we have this kind of simulation. And as you can see here, it is in good agreement with the experimental results that we have obtained. Also, from this experimental data, we can extract another special features to analyze the behavior of the quantized heavy electrons. And we can extract another information. So we measure first the energy spacing, as you can see here. So my mouse is not working here. Okay, between consecutive levels, as we represent here with this arrow, and we plot here this spacing as a function of the energy, and here I put the average value of these values as a function of the length of the width of the terrace. Okay, this is just the values that we get from this terrace. Okay. I'm going back to this plot in the next minutes. So we also know that measuring the energy widths here, the energy widths of the quantized resonance, we can get information about the scattering properties of the electrons. And this energy level broadening, gamma, that we call here gamma, is related to the lifetime of the quantum states. In this case, again, just for this terrace, here we represent with the orange color, and the green line represents the behavior of a perfect two-dimensional electron gas without interactions with the bulk, okay? And the blue line that we put here is the predicted behavior for a Fermi liquid theory, and it includes the inelastic electron scattering with the electrons from the bulk. And as you can see, the blue curve fits better our experimental data. So, which means that we have more contribution of the bulk electrons to the surface. And finally, we also analyze the step states, and we use, again, my mouse is not working yet, and we use this expression to fit our data at the state H, and measuring the energy and the spatial dependence of this state with this sigma sub E and sigma sub X that we mark here. And also I plot here just the values that corresponds for this terrace. Okay. We with this analysis, we also do an analysis on all the surfaces. For example, here, oh, sorry, my mouse is locked sometimes, sorry. And we analyze this conductance line that I put here as a white line. And here you can see the profile across the topography. And as you can see here that we have different terraces with different lengths, okay, with different widths. So we did the same analysis that I explained here for these terraces for the other terraces that we have here, for this one, this smaller one, and this tiny surface that we get here. And doing this analysis, we observed that here in the plot that I showed you at the beginning, that we complement this plot with the values from the other terraces, and the energy spacing between adjacent levels is proportional to this expression, as you can see here, is proportional to 1 over L squared. which is consistent with the quadratic behavior, with the quadratic band dispersion energy that we have. So also, the energy and the spatial dependence of the edge states as a function of the torus width also is plotted here. And we observe that in energy, the width of the step edges, the edge states, sorry, are inversely proportional to L, okay, where L is the width of the torus. And the width of as a function of the distance, they don't have L dependence, okay? This work is a work that is in progress, so the message to take home is this: we have experimental evidence of the quantum confinement of a heavy fermion system on the surface of uranium-ruthenium-2 silicon-2, and I don't remember say that all these measurements were done at 100 millikelvin. Okay, so with this, I would like to conclude just with these few points. We observe one-dimensional charge density wave as a result of the strong interactions between the atomic lattice and the wave vector Q1 due to the cracking process, due to the cleaning process that was done in the hidden order phase. Okay, and also the periodicity that we found can be explained by a fractional moiré pattern between these two vectors, and we suggest that controlled fracture can be used to create new ground states. And finally, in the last part, I show you that we have experimental evidence of a quantum confinement in a heavy fermion system, in this case on the surface of the uranium-ruthenium-2 silicon-2. Finally, I want to thank the people that have been involved in this research. In particular, I want to acknowledge to Herman Suderov and Isabel Guillamon, and the people from Grenoble, which provide us the sample, and the people from Colombia that also help us with the theoretical calculations. So thank you very much for your attention. I'll be happy to try and answer any question. Thank you very much.